Transitioning from analyzing just the graph of f of x to looking at taking the derivative of f of x, which we call f prime of x, graphing f prime of x, and looking at its features and relating it back to the graph of f of x. So this week we're looking at the relationship between f prime of x and f of x. For all of these slides and in your notes, I'm going to present the original problem and then the solution. These come directly from Delta Math, so as you're working through your problems and possibly watching videos or looking at the answers if you're getting them incorrect, they should match to the same format, which I think will be helpful for you. If we start with example 1, you're going to be given a graph. Notice in the right-hand corner, this is the graph of f. So this is your original f of x graph. You are to determine all of the x values for which the graph has a local minimum on the open interval from -9 to 9. So remember, intervals are the x values from -9 to 9, so the graph only runs left to right from -9 to 9. And when they ask you for local minimum, recall this means the valleys of the graph. Local maximum are the mountaintops. They're not absolute necessarily. They may be, but doesn't have to be that way. We're looking at the behavior of the graph between -9 and 9. If we bring up a partial answer key, we can see that the only valley that we see in the graph of f is down there in the lower third quadrant. It's highlighted in that circle. Okay? To present the correct answer, we are looking for the x value of the minimum. In this case, the x has a local minimum when it is -4, which would be the correct answer. Moving to example 2, we could be asked to determine all of the intervals for which f of x is greater than or equal to 0. Notice you were also given the graph of f of x. When you read the math language of this, you really need to clue into what they are asking. So let's go back to when we first did functions. F of x is function notation that represents the y variable. The y variable, we know, is plotted along the y-axis, the vertical axis. So when they say the intervals in which f of x is greater than 0, take a look here. We're looking for all of the parts of the graph, so that's the curved squiggly line, if you will, that are located above the x-axis because they have all y values that are greater than or equal to 0. The equal to 0 part is what we call the zeros. They are the x-intercepts. So in this case, we should include them. So notice f of x greater than or equal to 0, we're looking for where y or f of x is positive. Okay? The answer to this is on the interval between 2 and 6. If you pick any x value, you're going to have a y value that is greater than 0. So for example, let's take f of 3. F of 3, I would go to x on the 3 axis, I would go up. F of 3 is approximately 2.2, let's say. 2.2 is a positive number, so it meets the qualification of f of x being greater than or equal to 0. The final answer to this is the 2 is less than or equal to x is less than or equal to 6. Example 3, determine all of the x values for which the graph of f has a relative max on the open interval -9 to 9. Taking a look, we're analyzing for mountaintops. Maximum relative maximums. So between -9 and 9, I only see 2 mountaintops. Notice they're highlighted by the circle. The question is, where are they exactly? Our answers are the x values. So I'm going to unhighlight the final answer. And notice that x has a relative maximum at 2 locations, when x is -3 and when x is 5. Moving on to example 4. Given the graph of the function below, determine all the intervals where f prime of x is less than 0. So that prime makes a difference. That is not a typo. If you recall, whenever we talked about f prime or the first derivative, I tried to sink into your head that that means slope. So when I read the problem, what it's saying is on the interval between -9 and 9, looking at the graph, where is the slope less than 0? Less than 0 means negative. Negative slope means it goes downhill. So notice on the right-hand part of the graph, my slope is all negative for all of the tangent lines on F. So that pink box that's highlighted, it's going to be the location of that. We just have to then unhighlight the answer, and you can see that between 0 and 9, because my graph only went from -9 to 9, on that interval specifically, I have a slope that is negative. I have decreasing values of y. Moving on to example 5. Now, we're going to ask a different question. On the same interval, -9 to 9 of this graph, determine all of the values where f prime of x changes sign. So remember, that means where slope can go from either negative to positive or from positive to negative. Both of those indicate a change in the sign of the slope. So if we pull up our graph, I notice 3 places where I have mountains and valleys. The mins and maxes we talked about in the earlier example, relative min and max, are the location where slope changes from positive to negative. Remember, in those moments, the slope is 0. So as I analyze this, I then need to write my answer in the correct form for delta math. So the x values where the slope changes from negative to positive or positive to negative are at -5, at -1, and 3. Next example. Given the graph, determine all of the values on the open interval where f prime equals 0, but f prime does not change signs on either side. So comparing it to the last example, we were looking for negative to positive, positive to negative. Now what we're going to see is we can actually have key points on the graph where the slope is 0. However, the slope on either side does not change signs. Let's look at this a little bit more closely. Notice on the right-hand side, I have a decreasing slope. It's negative, 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 negative. But at some point, I have a leveling out point. Okay? Oftentimes, when you are asked a question like this, you need to think about what you remember as the graph of x cubed. Notice how it comes down, changes direction, but keeps in the negative direction, decreasing slope. You'll find a different name for this in subsequent lessons, but for now we just need to be able to identify these quote-unquote flat points where the slope is negative on the left, negative on the right, or in some cases positive on the left, positive on the right. That's not what's going on at example 6. The answer that we would be looking for this problem is when x equals 5 is where we have one of those points. Now I have one more example that is not in your notes that I want to talk about that's a little bit more complicated. So in my extra example, above the yellow line, I'm given a graph, again from -9 to 9. I'm going to determine the intervals in which f prime of x is greater than 0. So that translates to where on f of x do I have slope that is positive. However, that part of the graph has to have f of x less than 0. So if you remember from an earlier example, f of x is our function notation for y. So I'm looking for y less than 0. Well, that only occurs in quadrants 3 and 4 because that's where y is negative. The y values in your x comma y ordered pairs are negative in quadrants 3 and 4. So then I look at my graph and I say, oh, you know what? Look at the purple region. Between -9 and -4, I have positive slope, but y is negative. And then in the right-hand side, in quadrant 4, between 5 and 7, I have increasing or uphill slope. So the final answer that I would be looking for are these two intervals. I encourage you to try your answers in Delta Math, watch the videos that are there, and ask questions if you're still not getting the right answers. Good luck.